This is a Renaissance depiction of a cheetah or a leopard, and you can see there that it's well made. This is a ancient Greek version of a leopard, and you can see there too that it's well made, but with a different style, using mosaic style. This is the ancient Egyptian version of a cheetah or a leopard, probably a cheetah, and you can see there its size. This is a Mughal depiction of a cheetah in India, using the style of the Indians mixed with Persians and some Chinese influence as well. This is the Native American, I think Mayan or Aztec depiction of a cheetah. I mean, a jaguar. And you can see there too that they have their own interpretation of what it looked like. This is more of a carving than a painting. This is a Japanese interpretation of a leopard, and you can see here again, completely unique style, completely different than the other ones of all the paintings and that one carving by the Americans. But would you believe that this too is a cheetah or a leopard? And you can see the leopard here right in the middle, and you can see its ears at the over there. But something that you might have missed is that the part in the middle might be a leopard, but the sides are actually two cubs. The thinner ones are two cubs lying underneath the mother. These are Sona graphic styles which can be utilized to draw, but a lot of the time they're used for mathematics and culture and storytelling and a form of literature. This type of mathematical, graphic, and storytelling version of art is mainly found in Zambia, and it was practiced thousands of years ago. And we can see with other traditions, even housemaking, that this is throughout. You see the dots in the middle, those represent a starting outline, and then you draw around the outline with the finger on sand or with a pen or paintbrush, whatever, if you have those, as some did. And so this is how you make these graphic. And here's the thing, their mathematical implications are obvious. You can see how you can get your very complicated geometric shapes. This isn't Euclidean geometry. This isn't very simple shapes. These are very complex, and they represent something bigger than that, like prime numbers, multiplication, and division. As cool as it is to know that things like this exist, it's also important to know how it is made. So a simple explanation would be you get three dots, right? Put it on a graphic thing. So what you have to do is turn whenever you hit a wall. So we go like this, and like that, and like that, and like that. So that's the most simple version of this. But let's erase that and make it a little more complicated. Let's put 6 dots. Start again. So you start here. When you hit the outer perimeter, you turn. Go like that. Hit the outer perimeter, you turn. Go like that. Hit the outer perimeter, then you turn. Go like that. Hit the outer perimeter, and you turn. You can see here that this is the shape that is built by just doing this simple algorithm, and it is an algorithm. Some people call it the bouncy ball algorithm, because you imagine you have a square on the outside, and every time it bounces, so you can see if we go like that, it bounces and it goes backwards, and then it goes straight until it bounces, then it go backwards. Now let's do it again. Now here's the mathematical implications of it. You saw there that I could draw without lifting the pen up. I can draw the whole thing. So here's the mathematical implications. This is 9 dots. Now here's the problem. 9 dots equals a square. But we know that a square is times itself, right? So the number of lines you can make is the greatest common divisor, meaning whatever number these two sides, this side and that side, can divide into, the greatest number, that's how many lines or how many circuits you're going to have to complete. So let's do it as an example. Let me change colors so you can see it easily. So we do it like that. Hit a perimeter, then we turn. Right? So that's 1. Go like that. Hit a perimeter, then we turn. Okay, 2. Right now we got 2. So now we start from here. Let's change the color again, just for good measure. You go like that, you go like that, you go like that, you go like that. That's what we have. So it took 3 different lines, which means the common divisor of 9 is 3. Now, this might seem strange, like why would the common divisor of 9 be 3, but the other ones it was both 1? Well, common divisor can actually, in other words, you can get a prime number that is very high and still only take 1 root, meaning that the common divisor is 1 in itself only, which means you will only have to do it once. Now, here's the trick here. The trick is, because these people would know how to do this, they would know just by looking at it. Now, from now on, when you see this shape, you'll know it takes 3 of these to make this. And so now you already know the common divisor through memory. And of course, I can extend this to be more artistic. I could add a tail. I could add claws. Maybe even add a head if I want to. Right? And it becomes more of an artistic thing. But this is not necessary for the thing that we're doing. Let's do another one. So here we have 3 times 5. We can see here 3 times 5 because it's got 3 on one side and 5 on the other. But let's draw it and see what happens. So if we start here, we move like that, we're going to turn. There's no border, so we keep turning. We go up, up, up. Okay, nothing else to go through, so we go down. Nothing else to go through, so we have to turn again. Nothing else to go through, so we have to turn again. Nothing else to go through, so we have to turn again. You can see nothing else to go through, so we turn again. Every time we hit the outside perimeter, turn. Again, nothing to see here, turn. Nothing to see there, turn. Nothing there, turn. Nothing there, turn. Nothing there, turn. Should be more straight, but turn. Nothing there, turn. At the end of the day, this is what you get. Did it with one movement, not multiple colors. You can see, because you follow the algorithm, you get what you want. Now, there's a lot of implications here. You can see that it's symmetrical, first of all. Well, relatively, my drawing isn't that great because I'm using tablet, not my hand, not a proper hand. And you can also see that almost all the time, let me use a different color to illustrate this. Almost all the time, this will be in between four. One, two, three, four. And you can see here it's true as well. Even here it's true as well. 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 So let's delete those. But then it also has this like pineapple effect. Like it kind of looks like the pineapple. And this is because nature does these type of fractals is what they call it. So you can imagine if I had 300 going down this way and I had 500 going down the other way, that it would look something similar to this. Now, of course, um, the highest common divisor of 300 and 500 is not 1, but this is basically one where it fits, where the common divisor is 1, and you can figure that out easily. Now, of course, what a lot of these guys would do, depending on your culture, is they would add an aesthetic to it. So they would give it any other name. This one looks more like the leopard that we looked at in the beginning, but we don't have to use the leopard. Like all art, you can have your own interpretation of what it is. To me, it reminds me of the huts, Zulu huts, and of course you can tell that it's got the same. If you cone it, which fabrics are made straight, if you cone it, you will start to realize that this is a very easy way of planning to make those huts that are sort of roundish like that. And then they have those bars like that. And then they do that. Which it's important to plan this early because if you get it wrong, things could go way wrong. This part here would be this part here. Um, the second part, again, this would be way bigger because of the thing, but the second part would be this part, right? And then if there was a third part, if it was bigger, it would be like that, right? And then the fourth part would be another square in the same way. So all of them falling at a straight angle, right here. This is an easy way of planning these huts without um, needing too much and using basic mathematics. Usually these huts are built in circles, by the way. Makes it very difficult to do. And so building a intuition for geometry is very important. Of course, you can imagine that if you had a hut that was like that, right? And you built the first one, line in the beginning, right? But then you built the other one too close, and then the other one too far, that it would be uneven and it would start to take a shape that you don't want. So it's important to make sure that the shapes are even. Now, I'm not going to lie to you, when these things get really complicated, there's no way I could just do this myself. As you can see over here, you see the same geometric implications, but again, this is in basket form, and you can see that you can start making pictures. I promise you, you can make like a lion with this or anything like that. This is where it gets too complicated. You see how these flower petals, they form this thing. So this is staying true to the geometry, but not staying so true to just the math part of it, but trying to formulate pictures and having arbitrary turns at some points. And so you could, by doing this, create a picture of a lion or a picture of anything really. But just because you can do it doesn't mean it's a great idea. You can see here with the baskets made by these African women that there's more of a appreciation for forms that are less realistic because they represent realistic things almost like literature would. You see also these spiral patterns. Something you'll start to notice with these, first of all, fractals, and then also these geometric patterns, is that they have strong, and you will see it more in other ones, but these ones have it a little bit less. They have strong illusions going on, optical illusions going on. So you'll see here, if you don't concentrate, you'll start to see the effect as if it's rotating, as if it's moving. If you move your head back and forth, especially, it will look like it's rotating, but it's actually standing still. These things people would have great appreciation for. Just look at that. Think about how long this would take using the dot method. You just place a bunch of dots, move at an angle. Some of these, of course, are not moving at the exact angle, and also the dots would be placed in very like strange places in order to get this effect. But you can see that almost everything is not straight. You don't see it. Everything looks like it's in this one. Everything looks like it's falling into the center, creating this movement. And you see how the arrows are pointing, almost increasing the effect of falling in, even though these four squares are the same side on the outside and the inside. When Europeans first realized that this is what the Africans were doing and weren't just naive, as you can see, they're not trying to paint and they're just failing. This is a naive art, right? Where someone is trying to paint a picture, but it's not looking the way they want it to be. This is perfectly done for what they're trying to do. When the Europeans realized this, they decided we can't not put this in our culture. We can't not have it as part of the modern world. And so instead of looking them as behind, they looked at them as ahead. And that's why some documentaries from the past, you will see them talk about African art as being futuristic. Today, most people are familiar with these abstract forms, so most people don't talk about it. But back then, it was huge. By the way, what I've shown you isn't even close to the most difficult thing that they were doing back then. This is actually the simplest one that I can easily replicate. Now, there's other tricks that I'll use later, but if you see this trick, just know that the Africans invented it first. Now, I've seen other cultures in the world utilize it, but the Africans used it first. And you can see here that it's only a small number of people who do it this way specifically for the maths, whereas the other people, they sort of adopted the dots afterwards when they realized that that was an easy way of figuring it out. Next time, we'll look at fractals, and as you can see here, according to Ron English, university professor and author of African Fractals, Modern Computing and Indigenous Design, this was not simply unconscious or intuitive. Africans linked these fractal designs to concepts such as recursion and scaling that exist in African indigenous knowledge systems. Now, the consciousness of fractals in the European life was in the 1900s. So this shows you that there was a renaissance going on in Africa prior to any renaissance going on in Europe.